All right, folks, exciting day here, section 2.7, derivatives and rates of change. Now, I will tell you that, again, like I said just a second ago, sections 2.7 and 2.8 are all about derivatives, and I believe there are only 8 sections within chapter 2. So there's only 8 sections. We only have 2 more sections to go before we're completely done with chapter 2. But this is where we learn how to find a derivative and really what a derivative is. You know what a derivative is, we just haven't defined it yet, okay? We learn about what a derivative is, how to find it, the long way of how to find it. And then all of chapter 3 is about derivatives as well. Okay? If I had to put what is calculus? Like what is calculus 1? I say calc 1 is all about finding derivatives and finding integrals. Okay? Finding derivatives and finding integrals. Derivatives is the main topic of the first semester. Integrals is the main topic of the second semester. Okay? So let's talk about section 2.7, derivatives and rates of change. The problem of finding the tangent line to a curve and the problem of finding the velocity of an object both involve finding the same type of limit as we saw in section 2.1. Think back to our very first day of chapter 2. We worked with 2 problems. The tangent line problem, where we said, okay, we have this parabola, and I wanted to find, the slope at 1, 1 in that parabola. Remember, and we estimated that. We got closer and closer and closer to it, and that's how we investigated the idea of a limit, right? That's how we introduced the idea of a limit. We had this parabola, and we were saying, okay, we want to get closer and closer and closer to the slope. We want to figure out what the slope is. We said, okay, if we're looking at 1, 1, we want to find, okay, work along that parabola until we reach that point and figure out what the slope would be. We did that same thing with the velocity problem, right? If I wanted an instantaneous velocity, I wanted to get closer and closer and closer to that point where that velocity would be the exact amount. That type of limit is called a derivative. You didn't really understand that you were finding it, but that limit is a derivative. Okay, that limit is a derivative. That's really what the definition of a derivative is. Okay, we will see that it can be interpreted as a rate of change in any of the natural or social sciences or engineering. Derivatives have a wide variety of implications. Okay, the main thing that we're going to talk about, the main topic that we're going to relate it to is physics. Okay, so if you are in physics, this will make sense to you a great deal. There are a lot of other different topics that it relates to, though. Like if you know, or if you study a great deal economics, you can talk about derivatives within economics too, and I kind of hint at it later on today. Okay, so let's talk about the whole tangent line problem, right? That tangent line problem where we had, okay, if we've got that parabola and we were trying to get closer to the slope, what is that, right? Okay, if a curve has an equation y is equal to f of x, so just some function, and we want to figure out the tangent line at any point of that function. Now, and this is really important that I say you're looking for the slope of a tangent line at a point, okay? You're looking for the slope of a tangent line at a point, and that's very important that I say at a point. Because I could give you some weird, wacky curve, and I say, what's the derivative? And that does not make any sense. If I say, what's the derivative to a curve? No, you can't do that. Because I need to say, what is the derivative at point this? Okay? What is the derivative here? What is the derivative there? You need to specify where you're finding the derivative at, because it'll change depending upon the curve. Okay? So I need to say a given point. So we want to find the tangent line to C at the point P of A, so that's the point, P, A comma F of A. So that point A, X value is A, and F of A. Wherever I plug in that X value, that's what I get out. Now, to start out chapter 2, we said, okay, consider the slope. What was the slope? Well, it was F of X minus F of A, the two Y values subtracted from one another, divided by the two X values subtracted from one another. That's just like a plain old slope formula, right? Y minus Y over X minus X. But then what we did is we let that A value get infinitely close to X. right? We let that a value get closer and closer and closer and closer to x. And that's, again, how we study the idea of a limit. That's how we introduce the idea of a limit. We let q approach p along the curve by letting x get closer and closer to a. If the slope approaches a number m, then we define the tangent to be the line through p with slope m. Okay? Now, this tangent line, let me scroll it down here, is really the limit as x approaches a of f of x minus f of a over x minus a. Okay, that slope of the tangent line is really the limit as you let x go to a of f of x minus f of a over x minus a. We hadn't really notated it like this before. We had understood it like this, but we hadn't really used the notation. We hadn't really said, okay, this is truly, okay, the limit as x goes to a. What does that mean? That means as I take the x value and I make it closer and closer to a, so say if I'm looking at point 1, comma 1, the x value is 1. As I take x and make it closer and closer to 1, as it goes to 1, the slope is going to be, okay, f of x, the y value minus the y value, f of x minus f of a, all divided by the x values, x minus a. Now, the idea here, though, could I use direct substitution to evaluate the limit? Well, if x is a, should I just plug in a for x? Oh, bummer. A minus a. So there's got to be something weird happening. We might have to do some weird calculations. But what I'm looking at here is just saying, okay, I really just am defining the limit as x approaches a to be the slope. That's really what we're looking at. If I'm looking for the tangent line, the slope is the limit as x approaches a of f of x minus f of a over x minus a. We're going to use this a whole lot. Okay, we are going to use that a lot. We're going to have another calculation of it too. Now, in our first example, we confirmed the guess that we made in example 2.11. This is chapter 2, section 1, example 1. Whenever you see that notation in your book, 2.11, that means section 2.1, example 1. Okay, let's talk about it then. We did this example on our very first day of chapter 2. We did this example on our very first day of chapter 2, but all we could say was, okay, I think the slope is going to be 1 because it looked like it was going to get to 1, right? We said, okay, look at the y values. Oh, it looks like it's going to be 1, so yeah, I think it's going to go to 1. But now what we're going to do is we're going to confirm that fact. We're going to confirm that fact. Okay, now how do I do that? Well, I'm going to use that equation that we had just had on the last slide. I'm going to calculate the limit as x approaches a of f of x minus f of a, all divided by x minus a. Okay. Okay, so what is my a value in this case? Well, I want the limit as x goes to a of f of x minus f of a, parentheses, all divided by x minus a. What is my a value? Well, what is the x value that I'm trying to get to? What's the coordinate? 1. 1, comma 1, right? The x value is 1, so therefore a is 1. Well, let's see if that makes any difference. The limit as x goes to 1 of f of x minus f of 1 over x minus 1. Well, I know what f of x is. F of x is just my function, x squared. Okay, so this is truly the limit as x goes to 1 of x squared minus, well, what is f of 1? What is the y value at 1? 1, right? It's 1, isn't it? 1 comma 1. If I plug in 1, I get 1 squared is 1, but again, it was given to me anyway. I know it's got to go to that point. Over x minus 1. So the slope of this tangent line, is the limit as x goes to 1 of this thing. Now, can I use direct substitution? No, but can I factor the numerator? Yes, so let's do it. So this turns into x minus 1, x plus 1 over x minus 1, which cancels, which leaves us an x plus 1. So that's the limit as x approaches 1 of 1 plus 1. Ooh. So that actually, I should have said x plus 1 because that is 1 plus 1, or just 2. See, back on our very first day of chapter 2, I could pull out the notes. I could, go back to the completed notes and look at our handwriting. But we said, okay, we're just going to keep evaluating the slope and evaluating the slope and evaluating the slope, evaluating the slope at intervals so that I could get closer and closer and closer to 1. Yes, I have 1. Now I don't need to do that anymore. I don't need to do that anymore because now I understand how to evaluate limits. Now we can evaluate limits. And now we can specifically say that the derivative of x squared at 1 is 2. Okay? That's how we'll be wording this. The derivative of the function, the derivative of x squared at point 1 is 2. Whenever you talk about the derivative, the value of the derivative is the slope of the tangent line at that point. Okay? So whenever you use the term derivative, you say that is really like saying that's the slope of the tangent line. The slope of the tangent line. Now, sometimes we're going to just have values. Sometimes it's just going to be a number, right? Because I actually am given a point. But sometimes it's going to be a whole other equation. Sometimes you can find the derivative and it gives you a whole other equation, which is then really cool because it gives you an equation that you could find at any point what the slope of the tangent line would be. And that's like all chapter 3. How do we find those equations? All right, we sometimes refer to the slope of the tangent line as the slope of the curve at the point. So you'll hear me use that terminology too. If I ever talk about the slope of the curve at the point, that is really the slope of the tangent line, which is also called the derivative. Okay, that's also called the derivative at that point. The slope of the curve, the derivative. We talked about this as we zoom in and zoom in and zoom in. It looks like that line as we get closer and closer to it. Okay. Now, there is another expression that I would suggest you write down for the derivative, for the slope of the tangent line, and it's right there on the bottom, and I'm going to explain it for in a second. Because these two equations are used interchangeably. The whole f of x minus f of a over x minus a is also used in conjunction with this. The limit as x goes to, the limit as h, where did x go? The limit as h goes to 0 of f of a plus h minus f of a all over h. I'll give you a second to write that down before I talk through it, because it's important to understand exactly what's going on and where those h's came from. Okay, so what we're going to do here is we're going to bring in a new variable. We're going to bring in h. And you know what h is going to be? H is going to be the difference of x to a. Well, what do you want to happen with x and a? You want them to be the same thing, right? You want x and a because I'm really going to evaluate the limit as x goes to a, right? So in other words, what we could say is, well, what if we let h be that difference? What should happen to h then? We want it to go to 0, right? If h is truly the difference between x and a, then I want h to be so small it's negligible. I want the h to go to 0. Okay, so if I say h is my x minus a, then look what I can do. I add the a over to the other side, and I get x is equal to a plus h. So I can rewrite my other formula. I can do the whole f of x minus f of a over x, I said a, but didn't write it, over x minus a thing. And in place of x, I'm going to write a plus h. Okay, so that is f of a plus h minus f of a, which, okay, that's the exact same thing that we have on the top of this new equation, divided by, well, what is x then? X is a plus h. A plus h minus a. Oh, how convenient that those a's cancel out. So the whole limit as h goes to 0, this new thing, it's really just a rewrite of my old formula, just changing what I'm taking the limit to. Instead of making the limit go to x to a, I'm saying make the difference between x and a be negligible. Make it go all the way to 0. Find the limit as h goes to 0. Make it small enough that there shouldn't be any difference between x and a. So we will evaluate that by taking the limit as h goes to 0 of f of a plus h minus f of a, all divided by h. This one is a little bit more useful because look at the denominator. The denominator is no longer a binomial, where it was like x minus a. The denominator is no longer a binomial. It's just a single term, which is usually just a number. And it's easier to evaluate when I have just a single term on the denominator. Okay. So that's why you see just an h in the denominator. Now, again, as h goes to 0, can I do direct substitution here? No. As I work through these problems, you're going to find that I need to do something to like get around direct substitution. I need to do some sort of algebraic work so that I can get around direct substitution so that I can't actually plug it in. Okay. All right, let's take a look here. Example 2. Find the equation of the tangent line. Find the equation of the tangent line. Guys, I will tell you this. That direction is like all of chapter 3. Find the equation of the tangent line of this, of that, and we do all sorts of different functions. Now, to find an equation of a line, what do you need? You need a point, and you need a slope. You need a location, and you need a slope at that location. Okay? To find any equation of a straight line, you need a point and a slope at that point. So what we're going to do is we're going to find the equation of the tangent line to that function. So it needs to be the slope of this function at, and I have to tell you a point, 3, 1. So I'm going to find the slope at 3, 1, then use that point to create my, use that point and that new slope that we're finding to create my line. Okay? So let's do it. Let's evaluate it. I'm actually telling you the answer already, but just ignore that. I like the image. Okay? Because this is really visually what we're doing. Here's my hyperbola. This is 3 over x. Right? Looks weird, funky two tails like this. And at 3 over x, with 3 over x, that's the function. I want to find the slope of the tangent line at 3, 1. I want to find the slope of that red line. How do we do that? Well, we need to find the limit. And I use this one. The limit as h goes to 0 of f of a plus h minus f of a. That looks like a c. Minus f of a all over h. Because what is that truly equivalent to? That number that I'm going to get out when I evaluate this is going to be my slope. This is truly my slope. Okay? All right, what's A? What's A? Remember, A is always the x value that you're looking at. Where am I looking? 3. So A is 3 in this case. There's my A value. All right, so now this means I'm going to evaluate the limit as h goes to 0 of f of, now I would say 3 plus h, but I'm going to make that h plus 3. Oh, you know what? No, I won't. I do it 3 plus h in my notes. I'm going to stick with that. Minus f of, well, a is 3. All divided by h. So again, can I do direct substitution? No. Let's find our way around it though. Okay, well let's plug in. Let's find f of 3 plus h. You all done?
I didn't finish that last question.
I'll have you finish one more.
Okay, cool.
Okay, 3 plus h. 3 plus h. Remember that notation, all I'm doing here is just plugging in 3 plus h. Go back to your equation, 3 over x. So this is really like saying 3 over 3 plus h. minus f of 3. Well, what is f of 3? If I plug in 3, what do I get? 1. But I was told that anyway, right? That was the point. Did I need to give you that y value? We could have found it, right? Sometimes I do, sometimes I don't. Just kind of depends. And again, we got that by taking 3 and plugging it into here. 3 divided by 3 is 1. All right, and now divided by h. So now all we have to do, because I can't do direct substitution, all we have to do is algebraically reduce down this equation. Well, how do we do that? Well, let's work with the numerator. Let's get common denominators. Let's multiply that 1 by 3 plus h over 3 plus h. So that'll get me 3 over 3 plus h minus 3 plus h over 3 plus h, all still over h. Distribute that negative in so we can have common denominators here, or so we can combine the common denominators. 3 minus 3 minus h, catch that, minus h, over 3 plus h, all still over h. Okay, cancel there. We got a negative h over 3 plus h, all still divided by h. Okay, I'm going to change that division, that divided by h, into a multiplying by the reciprocal. Negative h over 3 plus h. Instead of divided by h, I'm going to multiply by 1 over h. And I do that so that it cancels. So this is negative 1 over 3 plus h. And again, all I did was just manipulate this equation. Why did I manipulate that equation? Because I couldn't do direct substitution. Can I do direct substitution now? Can I actually plug in the limit as h goes to 0 of negative 1 over 3 plus h? Yes. So this is negative 1 over 3 plus 0. So negative 1/3. And that's my slope. That's the slope of the tangent line at point 3, 1. Now, all that work was just to find the slope of the line. That whole thing was to find the slope of that tangent line. Where? At 3, 1. So now we have to come and say, let's go back to algebra 1. We got slope at negative 1/3, 0.1, 3, 1, not 1, 3. And now we have to go back and say, oh, what's my line with a slope of negative 1/3 and a point at 3, 1? Now, here's what I am going to tell you guys. I know back in algebra 1 and algebra 2, you probably used the whole solve for b method a lot more than the point slope method. I'll tell you right away, the point slope method for our purposes here is going to be way easier. So this point slope method looks like this. Y minus y1 is equal to m x minus x1. That's point slope formula. Y minus y1 y minus y1 is equal to m times x minus x1. All right, so that just means y minus 1, negative 1/3, x minus 3. Now we distribute the slope. Y minus 1 is equal to negative 1/3 x plus 1. And we add the 1 over to the other side. Y is equal to negative 1/3 x plus 2. That's the slope of the tangent line. That's actually, no, I said that wrong. That's the whole equation of the tangent line at point 3, 1. Now, what would happen if I changed where I wanted the equation of the tangent line from? That would change my whole equation, right? Why would that change my whole equation? Because it changes the slope and it changes the point that I'm using. So every time you change the location that you're finding the derivative of, every time you change the location where you're finding the derivative, that will change the equation of the tangent line. Okay? Now take a look at the image up here. Yeah, they give it to you in this weird x plus 3y minus 6. Like that is y is equal to negative 1/3 x plus 2, but it's like, why would you ever write, what the heck is that? I don't even know what form that is. That's like so weird. I could see maybe x plus 3y equals 6 because that's like standard form, but that's weird. But ignore that. What I want you to look at here is look at the slope. Look at our equation, negative 1/3 x plus 2, right? Negative 1/3 x plus 2. Do you see the line? You know, we looked at it visually right off the bat to start it. But look, 1, it's up here, 2, y-intercept of 2, and a slope of negative 1/3. Down 1, right 3. Negatively sloping line. This will give you the equation of that tangent line at any given point. Okay. Now, we talked about the tangent line problem on our first day, but we also talked about the velocity problem on our first day, chapter 2, right? So let's see how the velocity problem relates to this. In section 2.1, we investigated the motion of a ball dropped from the CN tower defined its velocity to be the limiting value of average velocities over a shorter and shorter time period. We said, okay, we're going to drop a ball. And we're going to find its velocity at even intervals until we get closer and closer to where we think it should go. And then we decided that's sufficiently close. Okay? In general, suppose an object moves along a straight path line according to an equation, S is equal to F of t. Whenever I use an S, I'm talking about the displacement. Okay? Displacement, straight line movement. Okay? So, in general, suppose an object moves along a straight line according to an equation, S is equal to F of t, where S is displacement, directed distance, they call it, of the object from origin at time t. The function f describes the motion called the position function of the object. In the time interval from t is equal to a to t is equal to a plus h, okay, using that same type of notation that we used a couple slides ago, where we said, okay, going from x equals a to x equals a plus h, so really the h is like our difference in time, right? Going from a to a plus h, the change in position is f of x plus h minus f of a. Whoa, that seems really familiar. Wasn't that the numerator of our derivative? Yeah, f of a plus h minus f of a. See the figure here, look. I'm really calculating the position at time a and then time a plus h and then finding the difference of these two. Saying, okay, f of a plus h minus f of a. That's the velocity, that the time here, and then the actual displacement, that will calculate velocity, won't it? If I've got displacement and I've got time, displacement divided by time it takes to displace is velocity, is speed, right? I'm traveling 10 miles, that's my displacement. I'm going in 2 hours, that's 5 miles per hour. That's displacement divided by time. So really what that truly is the f of a plus h minus f of a, this, divided by h. That's the time it takes to get there, right? A plus h. So if I'm starting at 0 and going to 2 hours, that's 2 total hours. Maybe I'm trying to find the displacement going from 1 to 2, or the velocity going from hour 1 to hour 2, or time 1 to time 2. Well, then my h value would just be 1 because I'm looking at only my difference in time between the two. So f of a plus h minus f of a all over h, and that is our exact derivative equation, isn't it? That's velocity. Now, suppose we made that h get closer and closer and closer and closer to 0. Suppose I wasn't thinking about 2 hours. Suppose I wasn't thinking about 2 seconds. Suppose I wasn't thinking about 1 second. Suppose I wanted to make that difference in time get closer and closer and closer to 0. That is instantaneous velocity. So this is truly the limit as h goes to 0 of this displacement over time is truly my velocity. My velocity where? My velocity at a given time value. My velocity at a, where a is any point in time that I'm looking at, and I want to say, okay, where is the velocity at time 3? Well, that's h goes to 0 at f of 3 plus h minus f of 3 all over h. That will give you instantaneous velocity at time 3. If we can calculate the limit. And again, calculating the limit just requires us to do some fancy manipulation, fancy algebra work to try to get h out of the denominator to solve it. Okay? This means that velocity at time t equals a is equal to the slope of the tangent line. Because look, if I can have my velocity equation, then the slope of that tangent line, or that, excuse me, my displacement equation, then the slope of that tangent line is always going to be my velocity. Slope of the tangent line of displacement is always going to be my velocity. Okay. All right, so let's take a look again at this thing. Suppose a ball is dropped. This is one of the same things that we did on day 1 of chapter 2. Suppose that a ball is dropped from the upper observation depth of the CN tower 450 meters above the ground. What is the velocity of the ball after 5 seconds? This is the exact question that we did, section 2.1. What is the velocity of the ball after 5 seconds? Well, what am I looking at here? I'm looking at when A goes to 5, aren't I? I'm looking at when I want what is the velocity of the ball after 5 seconds? Yeah, I want my A to be 5. Now, what we're not told here is our falling object equation. It was given to us in the book, so I'm just going to give it to you here. The distance fallen, and those of you in physics will recognize this equation, is 4.9 t squared. If there's no throw, if there's no horizontal velocity toward it, if it's just dropped, that is the equation in meters, right? That is in meters per second. Okay. In feet per second, it's different. I think it's negative 16 or something, negative 16 t squared or something like that. But this is meters per second, 4.9 t squared. So that is our equation. That's our initial equation. If f of t is equal to 4.9 t squared, then v of t is going to be equal to, look, this is displacement, this is velocity. Then v of t, the velocity is going to be equal to the limit as h goes to 0 of t plus h, that's a t plus h, minus f of t all over h. F of t plus h minus f of t all over h. All right, but we know f of t. We know f of t. Okay, f of t is 4.9 t squared. So I'm going to find f of t plus h. All right, so 4.9 times t plus h squared minus f of t, 4.9 t squared, all over h. Sometimes my h is turning to n's. So let's do our fancy algebra work. T plus h squared. Again, you guys are going to find that we're going to do a lot of binomial squared. It might be a good idea to just know that any binomial squared is first term squared, double the product, last term squared. Okay, that is t plus h squared. And then we still got our minus 4.9 t squared all over h. Okay, let's distribute our 4.9 in. So 4.9 t squared plus 2 times 4.9 is 9.8 th plus 4.9 h squared. And then we have that minus 4.9 t squared. Ooh, what can I cancel? My 4.9 t squareds. Which is this now. That's equivalent to 9.8 th. 9.8 th, excuse me. plus 4.9 h squared all over h. Ooh. Can I factor out my h? Yeah, both of those numerator terms have an h. So this turns into 9.8t, and that's a cancel here, here, and here. 9.8t plus 4.9, just a single h. So what did I do there? I removed all of my h in the denominator, right? That was the goal. Because now what can I do? I can now calculate the limit as h goes to 0 of 9.8 t plus 4.9h. Well, if h goes to 0, what's the only thing that's going to be left over? 9.8t. So my velocity after time t, because that's where I started, is 9.8t. That's our velocity function. And you know what that is? You know what we just calculated but didn't really even know it? We calculated the derivative of our distance equation. The derivative of our distance equation is our velocity. And we'll find that later on, the derivative of velocity is actually acceleration. And we'll chain those things together by finding the derivatives in between the two. Now, we haven't even answered any of our questions yet. That's just a velocity function. I want to know what is the velocity of the ball after 5 seconds. All right, well, that's pretty easy then. Let's find v of 5. 9.8 times 5 times 5. So the velocity of the ball after 5 seconds is 49 meters per second. That's part A. Part B says, how fast is the ball traveling when it hits the ground? How fast is the ball traveling when it hits the ground? Well, excuse me. I need to figure out what time it hits the ground, right? Because if I can calculate what time it hits the ground, I can find the velocity. So we need to figure out what time it hits the ground. Well, it's 450 meters above the Earth, and I know the distance is equivalent to 4.9 t squared. Okay. This is going to calculate me, the solution to this is the time when the ball hits the ground. So 450 divided by 4.9, and I take the square root of that, and it's approximately 9.58. T is equal to 9.58 seconds. That's when the ball is going to hit the ground. Now, if I want to calculate the instantaneous velocity of the ball, the instant it hits the ground, that's v of 9.58, which is 9.8 times 9.58. Or 9.8 times this thing. I'm just going to do that in my calculator. 9.8 times my answer, which is 93.91. The book rounds it up to 94. 94 meters per second. Now that's a really powerful statement that we made right there. We started with just the distance equation. All we started with was displacement. And if we start with displacement, you can find instantaneous velocity at any point along the way just by telling me what time you need. Yeah, that's a really powerful statement. We can find instantaneous velocity when all we started with was our position. That's it. And I'll tell you right now, we can find instantaneous acceleration as well. Okay, later on, and we'll figure out how we do that. All right, I've bored you enough today. That was fun for me. I don't know about you guys. That was fun for me.